Section 6.3, Properties of the Trigonometric Functions. We saw in the last two videos, I guess, that some angles are what we call coterminal, right? When that happens, the values of all the trig functions evaluated at those coterminal angles are the same. So we're going to consider an angle 9 pi over 4, right? What angle is 9 pi over 4 coterminal with? Well, if we think about the unit circle, here's our unit circle, and I'm going to focus on separating pi, or the upper half of the circle, into 4, so that each of these pieces is pi over 4 large, right? And we start counting. We'll go 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, 9 pi over 4. So 9 pi over 4 is coterminal with pi over 4. Their terminal sides end in the same spot. Okay? So notice how we got there. 9 pi over 4, if we, to count again, we went all the way around, that's 2 pi, and then another pi over 4. So 9 pi over 4 is equal to 2 pi plus pi over 4, right? Which other angles are coterminal with pi over 4? Well, what happens if we go around another 2 pi, right? From pi over 4, right? So what I'm saying is let's start at pi over 4, let's go all the way around 2 pi, I'm going to end up at another coterminal angle, right? Alright, well, let's take pi over 4 plus, 9 pi over 4, pardon me, we already did pi over 4 plus 2 pi, that's 9 pi over 4. How about 9 pi over 4 plus 2 pi? Well, that's the same thing as 9 pi over 4 plus 8 pi over 4 with a common denominator. I get 17 pi over 4. I could also start at pi over 4 and go backwards to find a coterminal angle. Right? What if I went this way? Right? How far is that? Well, let's take pi over 4 and subtract 2 pi. So that's pi over 4 minus 8 pi over 4 gives me negative 7 pi over 4. So it turns out that we could say that negative 7 pi over 4, pi over 4, 9 pi over 4, 17 pi over 4, and we could keep going in both directions, are coterminal. That means they have the same trig function values, right? And notice we got all of those by going a multiple of 2 pi, around, okay? So because they're coterminal and have the same trig function values, right, we could say that the sine of pi over 4 is equal to the sine of any of these, 9 pi over 4, right? Or it's the sine of 17 pi over 4. Be careful, I'm not saying that the angles are the same. They are coterminal, meaning they have the same trig values, the same sine values, okay? Rewritten, we could think of this as sine of pi over 4 equaling the sine of, remember 9 pi over 4 is pi over 4 plus 2 pi. And 17 pi over 4 was pi over 4 plus 2 pi plus 2 pi again, so that's 2 times 2 pi, right? And because of this, the sine value of theta is periodic. So sine is what we call periodic, with a period of 2 pi times k, where k is an integer, right? Think of the period as the distance around the circle, right? It's kind of how far do you have to go to get to an angle that has the same sine value, or for any of the trig functions to has the same trig value, right? Okay, it turns out that any angle, when you take the sine of it plus 2k pi, I'm sorry, let me back up. When you take the sine of some angle plus 2 pi k, where k is an integer, that's the same thing as the sine of just theta, right? So here we're saying that the period is 2 pi k, meaning that if you go around any multiple of 2 pi from any angle, and then take the sine value of that angle, it would be the same as if you took the sine value of the original angle without having gone around 2 pi k. Cosine is the same, has the same period. So do cosecant and secant. Turns out, however, that tangent of pi k plus theta gives us tangent of theta. So you don't have to go an entire revolution around to get to another angle that has the same tangent value as any angle. You just go halfway, or pi, any multiple of pi. You could go all the way around because that would be a multiple of pi, but you can stop halfway. And similarly for cotangent. Okay, so those are their periods. Oh, I'm sorry. Yeah, that's right. Right. Now we can go back and do a problem that we did in the section point 2 video, the tangent of negative 13 pi over 6, using the idea of periods, right? So the period of tangent is pi times some integer, right? So what we have to do then to find the tangent of 13 pi over 6, or negative 13 pi over 6, is to write it as an angle whose tangent we know. How about negative pi over 6 and some multiple of pi? Yeah? Right? So I'm going to split negative 13 pi over 6 into negative pi over 6 and negative 12 pi over 6. Right? It turns out that negative 12 pi over 6 is a multiple of pi. It happens to be 2 pi. Right? Remember, k can be any integer, can even be negative. Okay? And because of the idea up here, right? If I add any multiple of pi to an angle and then take its tangent, that's the same thing as just taking the tangent of that angle. So this is going to be equivalent to the tangent of negative pi over 6. Again, I know that tangent is y over x, and the p for negative pi over 6, the corresponding x and y are square root of 3 over 2, negative 1/2. So I'll take negative 1/2, divide by the square root of 3 over 2, negative 1/2 times 2 over root 3, that's negative 1 over root 3, and rationalizing we get negative square root of 3 over 3, right? Which is exactly the same thing that we got the last time, using the unit circle instead of periods. Okay, now we get to do what I think is probably the funnest part of trig. We get to start talking about the fundamental identities of the trig functions. And we'll talk about more identities as we go on in more sections, but these are the fundamental ones, kind of the most important. Alright, they're kind of the rules or the laws that the trig functions follow. And we can use them interchangeably to solve all kinds of things. Cosecant of theta. We already know that's 1 over y, right? But we also know that y is sine theta, right? So the first thing we can say then is that cosecant theta, instead of being 1 over y, we can plug in and say it's 1 over sine theta. Yeah? So cosecant and sine are reciprocals. Interesting. Okay. We can similarly say that for secant, which we already know as 1 over x, and x, which we know is the same thing as the cosine, so secant theta is 1 over the cosine of theta. So cosine and secant are also reciprocals. You may have noticed this before. Cotangent of theta is x over y, and we know that tangent theta is y over x, so that must mean that cotangent theta and tangent theta are also reciprocals. Yeah. Similarly, we can say that tangent theta, because it's y over x, and y is sine, and x is cosine, we can say that tangent of theta is sine over cosine. And we can also say that since tangent and cotangent are reciprocals, that cotangent of theta is cosine theta over sine theta. Alright, so in total, these are the reciprocal and quotient identities. Don't worry so much about the names of the identities. You just have to memorize the actual identities. Okay, let's find some more identities. Yeah? Remember that the unit circle has equation x squared plus y squared equals 1, right? And we defined any point xy on the unit circle. Any point on the unit circle has coordinates xy equaling cosine theta, sine theta. That's how we defined them, right? For some theta. Right? If we look at all the thetas, all the points on the unit circle and their coordinates will be cosine of some theta and sine of that same angle. Right? So we can then plug them in for that. Plug cosine and sine in for that. So if x squared plus y squared equals 1, then cosine theta squared plus sine theta squared equals 1. Customarily, we write the exponent, when there's an exponent on sine or cosine or any of the trig functions, we write it next to the cosine or sine so that we can not have to write the parentheses. Okay? Alright. This is a very, very important fundamental identity. It's one of what we call the Pythagorean identities. Yeah, and there are a couple more. If I take cosine squared theta plus sine squared theta equals 1 and divide it, both sides, by the cosine squared theta, of course, if it's not equal to 0. Oops, I wrote this one wrong. Dividing both sides by cosine squared theta, I get 1 plus sine over cosine is tangent, so sine squared over cosine squared is tangent squared. 1 over cosine is the secant, so 1 over cosine squared is secant squared. Yeah. And if we take the original cosine squared theta plus sine squared theta and instead divide both sides by sine squared theta, squared. Cosine over sine is cotangent. Sine squared over sine squared is 1, and 1 over sine squared is cosecant squared. Alright, so all of these Pythagorean identities, along with the reciprocal and quotient identities, are what we call our fundamental identities. You must memorize these. Okay? In the next video, we'll do some problems with these.